All right, let's pull back the curtain on artificial intelligence. We're going to cut through a lot of the hype and get right to the mathematical heart of how machines actually learn. We'll be exploring two really foundational concepts: the perceptron, which was basically the first artificial neuron, and then reinforcement learning, the science of learning by doing.
So here's our roadmap. We're going to start with that simple building block of AI, the original neuron. We'll look at how it learns, where it hits its limits, and how it evolved. Then we'll shift gears to a totally different way of learning from experience. We'll dig into its mathematical core, and finally, we'll see how both of these big ideas are powering the AI that's literally shaping our world today.
Okay, so our journey starts with the perceptron. This idea came about back in the 1950s, and it's this beautifully simple model of a single biological neuron. You can really think of it as the original brain cell that laid the groundwork for all the complex neural networks we have today.
To really get what a perceptron does, let's start with the problem it was designed to solve. It's a pretty fundamental question. How does a machine make a simple yes or no decision? You know, when a bank has to decide whether to approve or deny a loan, what's the actual calculation happening behind the scenes that leads to that final choice?
Well, the answer lies right here, in this model of the perceptron. See, on the left, it takes in a bunch of different inputs, things like your income, your credit score, and so on. That information gets processed through a few steps in the middle, and then on the right, it spits out a single output. It's a surprisingly direct computational model of how a real neuron decides to fire.
So what is it technically? A perceptron is an algorithm for what we call supervised learning. And supervised just means we train it using data where we already know the right answers. Its whole job is to be a binary classifier, which is a fancy way of saying it learns to draw a mathematical line that separates data into two distinct groups, like approved versus denied for that bank loan.
Let's actually trace how the data flows through it. First, you have the inputs, say your financial details. Each of those inputs gets multiplied by something called a weight, which basically represents how important it is. A high income might get a higher weight, right? Then the net input function just adds up all of those weighted inputs. And finally, an activation function applies a really simple rule. If the total sum is above a certain threshold, it outputs a 1 for yes. If not, it outputs a 0 for no. Simple as that.
But here's where it gets really cool. A perceptron isn't just a static calculator. It actually learns. And that whole learning process is about intelligently adjusting those weights to make better and better decisions over time. So how does it correct its own mistakes?
The core idea is all about minimizing its errors. So when the perceptron makes a wrong prediction, say it denies a loan to someone in the training data who was actually creditworthy, it uses that mistake as a signal. It then tweaks its internal weights to make that specific kind of mistake just a little less likely to happen again in the future. The math behind this whole learning process is captured in this one really elegant equation. This is the weight update rule. You could say it's the engine that drives how a perceptron learns. Let's take a second and break down what's happening here. Let's deconstruct this. The new weight is just the old weight plus some kind of adjustment. Now, that adjustment is based on three things. Eta, which is the learning rate, that just controls how big of a step we take. Then there's x, the input value, and most importantly, there's the error term. Now, here's the clever part. If the prediction was correct, the error is 0, which means the whole adjustment becomes 0. The weights only change when the perceptron gets something wrong.
And this diagram just illustrates that learning loop perfectly. An output gets generated, it's checked against the correct answer, and if there's any error, that information is fed right back to adjust the weights. It's this continuous cycle of predict, check for errors, and correct.
So this single perceptron is a really powerful idea, right? But it has one very important limitation. It turns out some problems are just too complex for one little neuron to solve on its own. And this leads us to the next big step in our journey: building something way more powerful.
So here's the catch. A single perceptron can only draw one single straight line to separate its data. And that's fine for what we call linearly separable problems, but it completely fails when it runs into more complex patterns. The classic example that everyone uses to show this is the XOR problem, where it's literally impossible to separate the two categories with just a single line. So what's the solution? Well, what if you use more than one neuron? What if you arrange them in layers? This creates what we call a multi-layer perceptron, or MLP, and this is really the foundation of modern neural networks. By adding these hidden layers in between the input and the output, the network can start to learn and identify really complex, nonlinear patterns that a single perceptron could never hope to see.
This table really highlights the key upgrades you get with an MLP. Instead of that simple perceptron learning rule, MLPs use a much more sophisticated process called backpropagation. It's a clever way to figure out which neuron gets the blame for an error and then adjust accordingly. They also use smoother activation functions, which lets them learn in a much more nuanced way, making these continuous subtle adjustments instead of just changing when they're totally wrong.
Okay, let's take a breath. So far, we've been talking about supervised learning, where an AI basically learns from a teacher who has an answer key. But what happens when there is no answer key? This brings us to a whole different way of thinking about learning, reinforcement learning. And it's all about learning directly from interaction and raw experience.
The absolute pioneers of this field, Sutton and Bartow, defined it this way. Reinforcement learning is about learning how to map situations to actions in order to maximize a reward. So it's not about being told the single right answer. It's about discovering the best strategy for yourself through pure trial and error, kind of like how you train a pet with treats. To really get RL, we need to know the cast of characters. The agent is our learner. It exists in an environment. The agent takes actions, and in response, the environment gives it a reward signal. Could be positive for good actions, negative for bad ones. The agent's entire goal is to develop a policy, which is just its strategy for picking actions, that gets it the most total reward over the long run.
Okay, now for the math. How does an RL agent actually develop that strategy? How in the world does it calculate the best possible path to maximize its long-term reward? Well, that strategy is its policy. And as you can see from these charts, a policy isn't some fixed, rigid rule. It's actually a set of probabilities. In one situation, the best action might have a 25% chance of being chosen. But in a totally different situation, the best action might be something else entirely. The whole point of learning is to keep refining these probabilities until you find the policy that gets you the absolute most reward. So how does an agent figure out which policies are good and which are bad? The answer lies in this famous formula, the Bellman equation. This is the central mathematical tool in all of reinforcement learning. It gives us a way to calculate the true long-term value of being in any particular state.
Let's break it down. It's actually pretty intuitive. The value of your current situation is simply the immediate reward you get right now, plus the discounted value of whatever situation you end up in next. And that discount factor, gamma, is really important. If gamma is high, the agent is patient. It cares a lot about future rewards. If gamma is low, the agent is short-sighted, and it only really cares about the payoff it can get right this second. Okay, we've gone deep into the mathematical foundations, from the perceptron learning rule all the way to the Bellman equation. Now let's zoom out and see how these incredible theories are actually being used out in the real world.
This is one of the all-time classic examples of deep reinforcement learning. DeepMind trained an agent to play the old Atari game Breakout. Now, it wasn't taught any of the rules, its only input was the raw pixels on the screen, and its only goal was get the highest score. And through nothing but trial and error, it not only completely mastered the game, it actually discovered brand new strategies that human players had never even thought of.
And here we see the power of multi-layer perceptrons in a totally different domain. This system uses MLPs to manage incredibly complex internet traffic. By looking at all the network data in real time, it can dynamically reroute traffic to make everything run faster and more smoothly, a task that's way too complex and happens way too fast for any human operator to handle.
So our journey has taken us from a single, simple artificial neuron making a yes or no choice, all the way to complex systems that can learn from raw experience. And this really leads us to one final, huge question. If a machine can learn to master pretty much any task through trial and error, guided only by a simple reward signal, what are the ultimate limits to what it can achieve?